Okay, hi guys. So, um, I'm glad you could make it today. Today, I'll be going over the AP Physics C Mechanics course. I hope you find it interesting and helpful if you are planning on taking the class or just interesting in general. So, like I said, we'll be going over AP Physics C Mechanics today. So there are four different AP classes, four different AP Physics classes. So there's AP Physics C Mechanics, then there's AP Physics C E&M, which is Electricity and Magnetism, and then there's AP Physics 1 and AP Physics 2. So AP Physics 1 and 2 are classes that are algebra based, while AP Physics C, the two classes under that, are calculus based. So they both have to have you take, like, for example, you have to take AP Physics 1 before you take 2, and you have to take mechanics before you can take E&M. So in this, some people, so for me, I took AP Physics C Mechanics over the course of one school year, but I know in some places they take AP Physics C Mechanics and they take mechanics with E&M in the same year, so they condense all of this information into one school semester. So during this, I think for just personal advice, I think if you can, you should take these two classes separately because first of all, these classes are both all these classes are fairly difficult in their level. And also, the way the exam is scheduled, the AP exam is scheduled, usually AP Physics C Mechanics is right before E&M. So in this case, you're just gonna have to take one exam after another, which is, I think, a bit of a really hard task because that's a lot of time to be taking tests and you barely get a break in between. But that's just my thoughts. Some schools require that you take it together and other schools require that you take it apart. So some things, it might not be under your control. But that's just a general information about physics classes. Okay, so next. So there are 7 units in the AP Physics mechanics course. So as you can see, the percentages of how much it's tested on the exam is listed on the side. Yeah. So we'll be starting with Unit 1, kinematics. So kinematics start with basic calculus functions and being able to interchange between velocity, acceleration, and displacement. So there's a lot of calculus involved in this class. It's a very math-heavy class. I'm not going to be going over any of the calculus because it's a bit it's really deep and kind of hard to explain. But I'll just go over a couple simple things. For example, here's velocity equals displacement over time. So, or average velocity. So in this, you guys might have all heard this before in a very basic math class where speed equals distance over time. This is basically the same principle, but then it is also applied to acceleration, saying average acceleration equals velocity over time. But then there comes a problem where you're like, what if your velocity is continuously always changing? It's like in a curved line and you're trying to find the velocity at a specific point in time or specific, just any specific point. This is where your calculus comes involved and you see these D's. So this D basically stands for this delta right here, but just in infinitesimally small portions. So to the point where it's literally nothing, but it's still there. So that's just to help you define any specific point in time. Okay, and then that also applies to acceleration. And then we move on to constant acceleration equations. So these are 3 basic equations you learn in kinematics. So they apply to any situation that has any constant acceleration. For example, usually any problem set on Earth, you can use these equations for because just simply people take gravity as 9.8 meters per second squared. So having this is constant acceleration, so you can use all of these equations. I also want to talk about vector versus scalar quantities. So you'll hear this a lot in this class, and later I'll give you an insight into a couple things. But vector quantities are things that have direction, while scalar quantities are things that don't have direction. For example, let's say you have a ball. It can roll to the right at 5 meters per second, or it can roll to the left at 5 meters per second. So these two quantities, if it was like rolling to the right, it'd be like positive 5 meters per second, while if it was rolling to the left, it'd be negative 5 meters per second. So this has direction if it's different. So if it's positive and negative, it has direction, so it's a vector quantity. But if it was in scalar terms, then this 5 meters per second to the right or the left is exactly the same. So for example, like I just said, meters per second, velocity is a vector quantity, so it has direction, but speed does not have direction. Okay. So here are some practice problems that I pulled from some practices that I did. So here you have a lot of interchanging between acceleration and like distance acceleration and velocity. This is a lot of calculus stuff. Most of this unit that has anything like calculus related, you won't actually have to like on the exam figure out like, oh, how do you what's the answer when you interchange like position into velocity or something. They won't ask this. I'd say that most of this is just preparation for how to do calculus, knowing all the calculus basics, and then like being able to apply them to different actually more useful equations. So for example, this one is just straight up asking you to transfer between displacement, velocity, and acceleration. And then this one is just asking for average. So, and then this one's just a simpler problem that's just asking you to convert. So next is in the kinematics is motion in 2 dimensions. So I was talking about before how there's a ball rolling from right to left. So in this, you have instead of rolling from right to left, there's also like an up and down factor. So how you deal with anything with more than one dimension is that you just split it into its individual parts. For example, this picture right here, So basically, you have to split it into its vertical vectors and its horizontal. So for example, you only take into account the way it's going up if you're throwing it from that bottom corner, how it's going up, and then how it falls back down. You don't take care at all about how far it's moving or whatever, and then you do the up and down individually, and then you do the side to side individually. It's usually distinguished by some sort of variable after. I'll show you in a minute, but these same constant acceleration equations still apply to these situations, as well as the converting between velocity and acceleration. Oh, anytime you see these arrows on top of some sort of variable or something, this means that it has direction. It's a vector quantity. So here you can see that there's an I hat with a hat and a J with a hat. This signifies that this is a vector quantity. This is either a horizontal or a vertical quantity. So the I typically stands for anything going right to left on the x-axis, while J signifies anything going up and down on the y-axis. This is just help to keep your variables separate and allow you to work a little bit more organized. So in this part of the unit, you'll learn a lot about projectile problems and things that like require like shooting and stuff. Okay, now we're moving on to Newton's laws of motion. So I know a lot of y'all might have learned this like back in middle school. So the first law of motion, the way I've written it here is more in the way my teacher taught them, because it was easier to apply to physics instead of like the straight way it's written if you like look it up on Google. So objects have a constant velocity until acted upon by an unbalanced force. An unbalanced force is the first law. So basically, this is the law of inertia. You might have heard it as like an object in motion stays in motion, an object at rest stays in rest. So this basically means it stays how it's working unless it had some kind of force stops it. So the second law is an unbalanced force causes velocity to change. So this is the F equals ma, forces cause acceleration. So F refers to the net force, while A is the acceleration and m is your mass. Then in this unit, you also learn about friction. So a friction is an opposing force that, like, if you slide on, it causes something to like slow down. It's an opposing force. So there are two types of friction. There's static friction and kinetic friction. So static friction is, let's say you have two objects, they're moving at the same time. So if you have one object on top of another and you're pulling the bottom object, but the top is just resting there. So as the bottom's being pulled faster and faster, the top block will continue moving with the bottom one until a certain point, which is this threshold of motion right here, where it starts slipping. This is where the friction goes into kinetic friction instead of static friction. So it's kind of hard to explain, I think, like just explain it, but once you start doing like practice problems concerning these different types of friction, it makes more sense. So also we learn about free body diagrams in this unit. So because there are forces, the first step to basically any sort of question regarding like Newton's laws, or really just any sort of physics, it requires you to you need to draw out your thing and all the forces acting upon your object. This makes it easier for you to understand what's happening and be able to like keep in mind of everything that's going on. So this picture right here, you can see that there's a weight force, so mg, which is mass times gravity. There's a friction force. Here are your splits of the vectors of your weight force, and then there's this thing called normal force. So normal force is basically the pushback of when you do something. So for example, let's say I put a book on my table and it weighs m, or the mass is m. So since it's pushing, the book's weight is pushing down at like mass times the gravity, the table is also pushing up mass times gravity, the same amount. So that's what's called normal force. So the push back up, because the table's not buckling under the weight of the book. But let's say if I push down on the book with a force as well as having the weight of the book, then the normal force is the force that I'm pushing down at plus the weight. Furthermore, you have to be pretty familiar with trigonometry when you're learning physics, because there are things like, mg sine theta, mg cosine theta. You need to know how to split these vectors correctly, or else it'll be very hard to understand and very hard to grasp. So like when I started this class, I was like a little bit confused, which made this class a lot harder than it needed to be. So just knowing some simple trigonometry really well is very important. Okay, so here's just an example problem also. It's fairly simple. You're just finding the normal force and the acceleration. Here's a force right here. Again, about the trig stuff, there is an angle where you have to find like the different components. So it's important. Okay, then to the third law of motion. So for every action force, there's an equal and opposite reaction force. For example, let's look at these three blocks being pulled. When this block is weighing down right here, so when mass 2 is pulling mass 3, it's also mass 1 is pulling mass 2, means it's also pulling mass 3. So like there's two sides of the thing. So like if there's friction on to this side, then there has to be an opposing force to that side. Okay, then we learn about Atwood machines. So Atwood machines are just devices that are used to like demonstrate the very basic fundamentals of how forces work and how things move. So generally, in Atwood machines, there'll be some kind of pulley system with a string. This pulley and the string are all have no mass in this situation, so you can just focus on the masses that are there and how they move under different circumstances. So uniform circular motion is where objects are moving in a circle. So the uniform circular motion is where it's at a constant speed. See how I didn't say velocity, because velocity has direction, and since it's always moving in a circle like shown down here, the velocity is always changing. But the speed is always the same. So this allows for there to be, when you're spinning something, there's a pull through to the middle of how you're spinning it. So since there's a force towards the middle, there's also an acceleration towards the middle. So that's why, like, if you're spinning something really fast and you cut the string, it goes flying because that force is now gone. So for this is the the one situation where you can have an acceleration without changing the speed, because usually when people think acceleration, they think like, oh, something's getting faster, which means the speed's getting faster. But in this case, that's not true. So like I was talking about, that pull to the middle, that acceleration to the middle, that's it's called centripetal acceleration. It is defined by this formula right here. So centripetal acceleration is equal to velocity squared divided by the radius that it's spinning at. So there's also this thing that's centripetal acceleration is also equal to omega squared times the radius. So omega we'll talk about a little bit later in the rotation unit, but it's just that fancy W. Something to remember is that you never want to label circular motion or the circular centripetal force on a free body diagram, because it technically isn't actually a force. That you just need to remember. You're probably going to learn more in depth why, but you just need to remember, if you label this, you don't get your points. For example, on the exam, if you have something like, they're like, oh, draw a free body diagram of what's happening, and it's like moving in a circle. If you draw on the free body, if you draw on the centripetal force as a part of your free body diagram, then you don't get your points for that entire question. Okay, now we move to unit 3, which is work, energy, and power. So this unit is basically all about how to do Newton's things that like Newton's equations problems without having to use Newton's equations, because everything in Newton's equations, everything related to that has direction. It's a vector quantity. Because it has direction, you have to keep track of the positive negatives, the way that the two things are moving or the multiple things are moving. While in work energy, you don't have to worry about any sort of directional things or any sort of positive and negative thing, because everything here is scalar. So in simple terms, work equals force times displacement. This is only in the situation that force is constant. Sometimes your force, if you're like getting fast, if you're accelerating more, if your acceleration is getting faster and faster, then your force is not constant, and therefore you can't use force times displacement. That's where this this equation, first equation in a blue box, shows up. This is how, like, there's this integration symbol right here, which is part of calculus, which basically is just using calculus to be able to find a certain the work for anything that is constantly changing. So network is equal to kinetic energy, is equal to the sum of the change in kinetic energy. My bad. So kinetic energy is also defined as 1/2 times the mass times the velocity squared, which will come into use later. There's also, besides kinetic energy, there's also potential energy, which is what that symbol U is. So there's that complicated equation where the change in U is the integration of the force times the displacement, basically the same as that work equation. So there are two types of big potential energy. So there's gravitational potential energy and then elastic potential energy, which is the spring stuff. So in gravitational potential energy, you have mass. So remember the previous equation, which was force times displacement. Gravitational potential energy is basically that. So force in this case it's usually if you're dropping something on the floor from like a certain height. So the force is mass times acceleration. Acceleration is gravity. So the force is in times g, mass times gravity. And then you multiply by the displacement, which is the height. So mgh is how you find your gravitational potential energy. Then for springs, furthermore about potential energy, for gravitational potential energy, the closer to the ground it gets, the less potential energy it has. Okay. Then for springs, there's springs was a kind of a hard unit for me because I didn't understand it. But so you may want to pay attention to this one like during class. But springs have a special force. So the force of a spring is negative k times the displacement. K is the spring constant. So like one of those springs you have at home where you can just pull it out and like from like a ballpoint pen has a lower k than, for example, that garage spring that like pulls up the garage door. So that's just the spring constant, basically how stretchy it is. And then x is the displacement from the center. Then there's elastic potential energy. So the potential energy of a spring, it's 1/2 times the spring constant times your displacement squared. Okay. Then there's this important thing called conservation of energy. So this basically means that so everything we do in this class, almost everything we do is in a situation where there is no there's nothing. Well, in this unit at least, there's not really that much things that friction or like air pressure or air drag, stuff like that. So let me go to the previous slide. So during the spring one, this is all the force in the equations and stuff are in the situation that these springs won't ever corrode or they won't lose their springiness. They'll just stay the same forever, and there's no air drag, even though in the real world it's not like this. Okay, back to conservation of energy. So this means that our external work is equal to the potential energy plus the kinetic energy inside the system. So conservation of energy basically means at any point in the system, at any point in time, the kinetic energy plus the potential energy will always, at the first point, at the beginning, the kinetic energy plus the potential energy should be the same as the kinetic energy plus the potential energy at the end. So the first should be the same as the end. So for example, on this roller coaster, if it starts with this much potential energy, because at the very top, you haven't started moving yet, so you have as much potential energy as you can. You go down the hill and go all the way to the bottom. So at this point, you've lost all of your potential energy. Let's say that's the floor. That's as close to the ground as you're going to get, so you have no more potential energy. Because like I said, the higher you are, the more gravitational potential energy you have. But that means that you have to have more kinetic energy. You have to be going faster. And that makes sense. And that's how conservation of energy works. So if you come back here, your potential energy is more, but your kinetic is less. Something to note is that this is like a really important concept. So like, not gonna lie, if you're on the exam and you don't know what to do, then like if you write a conservation of energy equation, then there's a good chance that you might get points for that. That's how important it is. Okay, then there's power. So power is definitely not as important as work or energy in this unit. I don't think it's like tested like that much at all. But anyways, it's the rate at which work is done. So work per time. So it'll just be like how much work you do and how fast you do it. So like if you pushed a block, so this is like I have a little brother, and if I pushed a block like super fast from one end of the room to the other, but my brother pushed it just slower, we would have done the same amount of work, but we would have been doing it at different powers because I did it faster. Okay, and now to the next unit, which is systems of particles and linear momentum. So systems of particles starts with center of mass. So center of mass is basically you're just finding the center of mass, usually of like a system or something like, let's say this ball here. They're assuming that this rod does not have any mass, but these two balls do. So the way you do center of mass is you have some sort of reference point, which in this picture is at this line, and then you measure the distance from each mass to the line, and then you measure, and then you multiply the distance by the mass, and then you add them together and divide them by the total mass. This gives you the distance from that reference point. That gives you where the center of mass is. So theoretically, if you had this and you balanced your finger right where the center of mass is, it shouldn't tip over. So center of mass is usually helpful for like if you have some like big weird shaped particle or weird shaped kind of object. Center of mass allows you to do calculations a lot easier. You just find the middle of where that is and then calculate everything as if all the mass was in the center of mass. It makes it makes calculations a lot easier. So then there's impulse and momentum. So momentum is used with the variable p, and then it is equivalent to mass times velocity. Okay, so there's a relationship between force and momentum that I won't be going into, but basically the derivative of momentum divided by the dt. Yeah. But then there's a relationship between impulse and force as well. So impulse is the change in momentum. And so these all have a different sort of relationship that you'll be going into. And then the final part of this should be the final part, is about collisions. So in this class, there are 3 different types of collisions. Sometimes it's 2, categorized into 2. But basically, there's perfectly elastic collisions. So your momentum, mass times velocity, is conserved, and your kinetic energy is also conserved. This is usually when you have like 2 balls going at the same speed, and then like 2 balls going at a speed, and then they like bounce back exactly. And then, but then there's also inelastic. So inelastic is everything that's not elastic. So this is where only the total momentum is conserved. So this could be like you bounce and then they like both go in the same direction, or they bounce and like one goes fast and one goes like slow and stops, or like one stops and then the other one keeps on going, stuff like that. And then there's perfectly inelastic, where your objects end up sticking together and keep on going. So this sticking together means they have the same velocity, end up with the same velocity. Okay, anyways, so all of these different types of collisions have in common that their momentum is conserved, which means that the mass of the beginning times, okay, so mv refers to the first mass, so if it's two masses colliding, the first mass times the velocity it's going plus the second mass times the velocity it's going should be the same as the ending result. So if it's going this at the beginning, then the end result should be the exact same. Okay, then we have rotation. So rotation is just going in a circle. Anyways, so I said earlier that there is this thing called omega. So there are three symbols for rotational, or four. There are four symbols for rotational physics things. So the first symbol is theta, which is equivalent basically to displacement. There's omega, which is equivalent to velocity, and then there's alpha, which is equivalent to acceleration. There's also torque, which is equivalent to force. So these all have a relationship between them where like velocity is the radius times the times omega, and like displacement is radius times theta, stuff like that. There's also this thing called moment of inertia, also known as angular mass. So if you think about it, or in physics, you can't use mass when you're using rotation. Like you switched out all these variables, like you can't use acceleration, you have to use angular acceleration. Similarly, you can't use mass, you have to use angular mass or moment of inertia. Like if you think about it, let's say this rod is super long and it has the same mass as the super short rod. This really long rod, when it spins around, let's say there's an axis through the middle and it spins around, if you think about it, it'll spin around slower than if like all the mass is at the center and it just spins around super fast. This shows the you can't just use mass, you have to switch it up. So there's this formula where there are different levels of, like for different shapes, there are different types of angular moments of inertia. So this is usually given on the exam. You don't really have to memorize these, but it's good to know just for class or something. Anyways, so there's this general equations for that. Then there's this thing called parallel axis theorem. Basically means it's just a theorem used so that instead of having to know like, so for example, like these two rods are technically like this rod right here and this rod right here, technically the same, but the axis is through different points. So this equation right here is actually just equal to this I plus the mass times the distance from here to here squared, or which is also known as half the length. If you do the math, it works out. Okay, then we move on to rotational kinematics. So rotational kinematics, very similar to linear kinematics, just all of the formulas have been switched out. All the variables have been switched out. For example, any x's in the very beginning have now switched to thetas, or any omegas have now switched to, any velocities have switched to omegas, angular velocity. So in this, for example, now when you do outward machines in rotational kinematics, you have to take into account that this pulley has mass. This pulley has mass, it has a radius, and you have to figure out how to do stuff with that. You have to use your like things like your moment of inertia to find out things like how it spins. I think this unit was like complicated, but personally I like this unit because I thought it was fun and there was a lot of like applying of formulas and stuff. I took also a lot of notes on this one because there's a lot of stuff to know for rotation. Anyways, there's also rolling motion. So there's Newton's law is applied to rotation. So just like force, F equals ma, force equals mass times acceleration. Here, torque equals moment of inertia times alpha, or angular mass times angular acceleration. So everything is angular here. Rotational kinetic energy, again, very similar. You just change velocity to angular velocity, and then work energy, also similar. So in this unit, you also learn about rolling. I think everything done rolling here is on non-bouncy surfaces. So everything is rolling smoothly. There's only enough friction to let it roll back, because if you think about it, if a ball is rolling and there's no friction, it just won't roll. It'll just slide because there's no friction, and that's the only reason things roll. There's some like special things that you have to remember when you learn this that are opposed to like normal dynamics and stuff. So keep that in mind. Then there's this thing, conservation of angular momentum. If you think about it, like if you've ever watched like the Winter Olympics or something and watch ice skating and see spins, you see all like figure skaters start out with their arms out wide, and then they bring them in to go spin faster. So this is conservation of angular momentum. So basically, angular momentum, similar to normal momentum, but it's just angular mass times angular velocity. So basically, your spinning is always at like the same, so it always stays the same. So if your radius, aka a change in your angular mass or moment of inertia, if that gets smaller, then your speed, your angular velocity has to get larger, so it can conserve. So it's conserved. So that's why they spin faster. Here's another application on the bottom picture where it's actually in physics, where you might encounter it. So like at first you were going at the only one disk was spinning, let's say, and then you drop another one on top of it. Now they're spinning together. So then that means your angular mass has changed, and that means you probably go slower now. Okay, unit 6 is oscillations. Oscillations are basically waves, basically. So there are only 2 types of things that you learn in physics about oscillations, and you're either talking about springs or pendulums. So like I said previously, in here, like springs, they're always like, they don't have anything to stop them. For example, if you put a spring here and like you let it go, it'll just like go like this forever in physics. But in real life, that doesn't happen because there's stuff like friction and like gravity and like drag and whatever. But in here, everything's considered like perfect. So there's this equation here that gives you things to know. On the right is just what part is what. So you learn a lot of terminology in this unit, I believe. So like there's like how the amplitude, which is like how high the waves are, the period, so like how long it takes to complete one cycle, and then like frequency, and like you learn about the relationships. There are a lot of just formulas involved in this one. So there are 3 types. Oops, I spelled that wrong. There are 3 types of simple harmonic motion systems. So like I said, there's a mass spring, and then simple pendulum, that's 2. But then the mass spring can also be split into there can be a mass like that, like going like that, or it can be going up and down. So like I said, there are like a lot of equations in relation to how like frequency and period are related, and like the times it takes. And then there's also things like back to the potential kinetic and kinetic energy thing back from when you learn about springs. That's also involved here. So yeah, personally, springs, oscillations wasn't my favorite unit, but it was all right. And then the final unit you have is gravitation. So here you learn how basically everything pulls on everything else. There's this so the force of gravity is also like is always the gravitational constant. So the force of gravity between 2 objects is always the gravitational constant multiplied by the mass of one, and then also the mass of the other, and divided by the distance between them, or the radius between them, squared. So the two equations below are just for the radius for Earth, the radius of the Earth, and then so this is looking for the gravitational constant of our gravity around Earth, which is 9.8. So this is how you would figure it out. So it's just the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. If you do that, if you look up the measurements and do that, it gives you like somewhere around 9.8. Then there's finding stuff, the gravitational stuff, like from the gravitational force from somewhere not on Earth's surface, so like really far away, and then you can use that to figure it out. On the bottom is just a example. So in this, you basically learn that, like, for example, if you're standing next to a super big mountain with a lot of mass, you're like, gravity like attracts you to that mountain, but you can't feel it because like it's not the same as like the gravity of the Earth, because like that mountain is definitely not as big as the Earth, but it's still interesting to think about. You also learn about orbits of planets and satellites. So how like planets why they go in like an ellipse instead of in a circle, and like the different formulas for this. To be honest, I didn't really like this unit. It was kind of confusing. It kind of like doesn't relate to like any of the other units, but like also kind of does. Anyways, so now we're going on to reviewing like just the exam in general. So I went over this in the very first explanation, the very first presentation, but this exam has two parts. It has a multiple choice and a free response. So the multiple choice has 35 questions, 45 minutes to complete, and it's worth 50% of your final grade, while the free response has 3 questions. These 3 questions are like split into like 10 different parts though, so and then it's also 45 minutes, and it's worth 50% of your final grade. So if you think about it, or if you know, the physics is actually one of the shortest exams. I think it might be the shortest. It only takes 90 minutes for the entire thing, while like things like biology or computer science, like this is like 3 hours each. So this is a relatively short exam to get through. So it's a good reason why to take this class, I guess. So here's some tips and things to know. Well, obviously study a lot before the exam. So like I was saying, like this test is super short, so it's easy to do a lot of practice tests for study. The thing about also like since it's a math-based course, when you're studying for math, like it's different from studying for something like English, because math you have to know how to do stuff, like it's just like you have to like do practice problems to understand instead of just like reading your equations. So it's like you have to study a lot. It's math based. It's also like really hard. So the physics pass rate, I talked about this in the first presentation too, but the physics pass rate is really high just because this class is so hard. Or for mechanics and E&M specifically, that this classes are super hard. So they like scale up the scores a lot, so that almost like I think in 2020 40% of students got 5, which is like a really high percentage compared to like on biology or whatnot that they got like the percentage is like 6%. So like yeah, it's really high. But anyways, on the mechanics exam, I think on all physics exams, there's a formula sheet provided. So it has all of the necessary formulas, like just physics formulas in general, as well as any sort of calculus formulas to on the exam, but it doesn't explain each one. So it just lists out all the questions, all the formulas, and just like if you know what they mean, then you can use them. If not, then you can't. It's still good to memorize them though, because the way the exam is formatted, it's in like a booklet. So like if you want to go back to look at a formula, you have to like flip back and forth, which is takes up a bit of time. Anyways, And then there are things to remember on the here are some things to remember on the multiple choice question part. So again, at least half of this section requires like being able to apply formulas quickly and do math. So the thing about the multiple choice, a lot of it is they don't give you numbers for the multiple choice. It's either like strictly like conceptual, like requiring you to know how stuff would happen if just in a concept, or it gives you like some sort of, it gives you some numbers, but it doesn't give you all the numbers. So most of the answers on the most of the questions for the multiple choice require you to have an answer that has like a variable in it. So you aren't allowed, you need to know how to do stuff without numbers, like just variable. Also, another tip is, again, this is only like 45 minutes for 35 questions. You have like a minute and a half around to do every single question. So like if you're reading the question and you don't have an immediate idea of how to do it, just skip to the next question and keep on moving. Because usually, again, like further questions in the test may help you remember how to do one of the beginning questions. Also, like if you don't really have to keep, like, of course you have to keep track of time, but you don't really have to be like timing yourself like, oh my god, I have to do a minute and 30 seconds and if I can't do it under it, then there's a problem. So the thing about that is like some of the questions are like so easy, like to a point where you can like look at it and know the answer, but then other questions will take a bit longer. So just stressing about like each one keeping under a minute 30 seconds is a bit stressful and unhelpful. So like if you can read the question and have an idea of how to do it, then keep on do it until you finish the problem. You do all your scratch work on the test. So even if you get like halfway and you're like you get stuck, you can just skip to the next problem and come back and look at your work again. And then here's some things to remember on the free response question portion. So always put units. The thing about the exam is that sometimes you get points for putting units. It's like extra free points, basically. You get like points for putting units. And I mean, sometimes you don't, but like being able to get those free points for like literally just putting a unit is like super helpful sometimes. Also, when you're in doubt or you don't know how to do something, draw a free body diagram. It almost 100% of the time it will help with how you're doing it. Because free body diagrams, it requires you to like think when you're drawing stuff out, labeling all the forces. Even though it feels like a waste of time, do it and then you'll like understand. It'll help you understand what's happening and possibly like allow you to continue the problem. It's also preferable to do work symbolically. Oh, I skipped it. So if you start a question and you don't know what to do, so write down an equation that you think relates to the problem. The way physics is graded is not like, oh, you got the right answer, check, you get the point for the question. The way it works is that if you have the right idea or you go in with the right like process, then you get points for every single correct step, basically. That's like important, of course. So like you might start like if you write down, like I said previously, how like the conservation of energy, like a lot of the time you start out with that equation, you write it down, you get a point. If you keep on going, you get more points. So there's no point, there's like, you shouldn't try, like just skip a problem if you don't know, like might as well like try and write something down because you're probably always gonna get points. Like even if you get the final answer wrong, every step you did before, if it was correct, if it was like the right, not even the numbers don't have to be correct, but like the symbolic work is correct, then you get points for that. Also, there's this thing called continual error. So like, for example, because there are 3 questions, each question is split into multiple parts. Some questions depend on previous portions for answers. If you get question 1 part A wrong, but you go to question 1 part B and it requires an answer from question A, if you do everything question B right with this number from question A that's wrong, you still get all your points, even though technically the end result is wrong. Okay, then it's also preferable to do work symbolically. Keeping track of your variables sometimes is super annoying, but like instead of plugging, you can if you plug in the numbers at the end, you may be able to cancel out stuff and be able to plug it in faster. Of course, you do get a calculator on this test, so but it should be helpful to do your work symbolically first. Plus, it helps your grader, understand what you're doing. Also make sure to read over and answer every part of the question. Some questions, like even though there are only 3 questions and each question is already split into multiple parts, sometimes each part of each question has multiple parts. So make sure you are answering every single part to make sure you get maximum points. Also, you're allowed to skip around the test. It's not illegal. So being able to skip around is sometimes really helpful because a lot of people, like when they're taking tests, they go like from 1 to the end, start from 1, keep on going all the way to the end. But sometimes when you're starting, you see question 1 and it like you have no idea how to do it. So sometimes it's best to like skip around and start on like maybe question 2, gain up your confidence, be like warming up your brain kind of, and then end up finishing like with question 1. Just like the multiple choice, if you finish with the end questions might help you remember the first questions and you can keep on going.